Okay, so recording has started. So what I want to do next for you guys is go down to the bottom part of this paper and let's take a look at one of these work energy theorem problems. Okay? So we said that work energy theorem applies in a situation where we have a non-conservative force. Non-conservative force is anything besides gravity or springs or elasticy forces or something like that. Okay? So let's take a look at question number 2 down here at the bottom. Alright, so there's question number 2. And it says, a crane does 1,310 joules of work on a 500 kilogram bundle of steel to lift it from the ground to the top of a platform. How tall is this platform? So, first, we said the first thing we should do is what? What are we asking? What are we looking for, right? So what is this question asking for? How tall, right? So that's going to be which variable? Height. Which height specifically? Because where does the steel bundle end up? On top of the platform, right? So the height of this platform, that would be how tall is the platform? That's going to be our final height, right? Because that's where the steel bundle ends up. Okay? All right. Some obvious things that it tells us in the problem. So it's one obvious thing that it tells us that we have to work with in the problem. Amount of work, right? So 1,310 joules of work, right? Remember that work and energy have the same unit because work is just energy moving around. So we got to have the same unit because it really is energy that's moving one place to the other, okay? The next obvious thing that it tells us is the mass of the bundle of steel, 500 kilograms. So those are the two obvious things. Couple of less obvious things. Where does the steel bundle start? At the ground. So what is 0? Which height? Okay, so that's 0. Less obvious in this problem, all right? What was the bundle of steel doing before the crane picked it up? Is at rest, right? So the initial is 0, right? The crane picks it up and it moves while the crane is picking it up, but then the crane dumps it on top of the platform. What's it doing at the end of the situation? It's at rest again, right? So that means that the initial velocity is 0, but also final velocity is going to be 0. Okay? Good there. All right. Now, is gravity the only thing acting on the steel bundle in this problem? What does it tell you? There's a big crane, right? So the crane acts on that big bundle of steel. So now, instead of being able to use our conservation of mechanical energy, right, we have to use work energy theorem. That looks like this. Okay? It is open. All right, so we have to use this formula this time because there's a force other than gravity or something other than gravity that's affecting the steel. Now, you don't necessarily have to show me this every single time, but remember, right, mechanical energy is a combination of a bunch of different forces, whether we're talking about it being conserved or even if it's not conserved. So this equation we can rewrite to look like this. Okay? Does that make sense what I just did there? All right, just like we did in the conservation problems, right? A bunch of these terms are going to go away, right? First, just because in most of our problems we can do this, right? Anything being stretched or compressed in this problem? No, right? So that gets rid of initial elastic energy and final elastic energy. Okay? In our information that we figured out about this problem, what did we decide or what did we figure out about the movement of this steel bundle? What's it doing at the beginning? It's resting, right? So what does that mean about the kinetic energy at the beginning? This is 0, right? And we also figured out that when it gets to the top of the platform, what else is it doing? It's resting again. So the final kinetic energy is also 0. Okay? Where does this bundle of steel start? On the ground, right? What did we say about that height? The height on the ground was what? 0. So what does that do to our initial gravitational potential energy? If it starts at height 0, that goes away too. Does that make sense? Okay. And then that leaves us with W on the left-hand side and PEG final on the right-hand side. Because what did we say that work does? Work changes the energy of an object. So if it goes up onto a platform, it has more energy than we started with, that's work. Okay? But does that equation have the variable that we're trying to solve for in this problem? Indirectly, as it's written. As it's written, does it have the variable that we're trying to solve for? We're trying to solve for H final, right? H final doesn't show up in that equation. But we know that we can expand the potential energy out, right? Because we know that potential energy gravity is equal to mgh, right? And if it's the final gravitational potential energy, which height do we want? Final height. Okay. And then we can rearrange that equation. To look like this. Now we start plugging in things that we know into that equation. Right? We know the amount of work that was done, we know the mass of the steel bundle, and we know the acceleration of gravity. So we know all three things on the left-hand side of that equation, and we can figure out what the height is going to be. Is that good? Oh, one thing. I know you guys aren't really graphing, but if you're using the graphing calculator, right, make sure that you put that in parentheses, because if you don't, your calculator will do order of operations and it will give you a different answer than what we actually want. Okay? You guys have to use parentheses too, but. All right. So that's the answer your calculator gives you. How many sig digs should our answer have? Should have 3, right? This work, right, 1310 only has 3 significant digits because that 0 isn't significant, right? Because Kelly, it's at the end, sorry, it's at the end, but does it have a decimal point? No, it doesn't, right? Yeah. But this, right, because there is a decimal point in 500.0, all of those are significant, okay? So, good.
There's 1, 2, 1, 1.
gravity doesn't count, yeah, because that's not really a measurement, it's just something that we know. Yeah.
Classes just keep getting smaller and
Yeah,
smaller.
people
I mean,
people
first
just
period classes
drop.
had started with 5 and then got down to 0. Is that the goal here?
Big freshman field trip today.
I got you.
Freshman English field trip.
Gotcha.
So yeah.
I just thought I'd.
Yeah. So, although we've got a lot done today actually. I mean so I think we can safely say that when there's goofing off in the other period or goofing off and everybody else is here, it's not you three. Right? So believe me, if only there was a visual to that. I'm not gonna specify. I'm just gonna say if only there was a visual to that. If there was a visual to this recording, we'd be good. So, all right. Does that make sense? Okay. All right. So what I would like you to do this evening, and you guys have like 10 minutes now, so if you want to start it, you can. I would like you to try up on the conservation of mechanical energy part. I would like you to try number 5 and number 6. Okay, so 5 and 6. And then down at the bottom, the work energy theorem part, number 1 and number 3. Okay? So that's what I would like you guys to try for homework this evening. I will put the answers online, so the answers will be there for you, so you can check and see how you did. I will attach them as an attachment to the event that says homework conservation or conservation of mechanical energy, work energy theorem problems. So, okay, good there. Good class recording, everybody. Well done.